Thank you very much. First of all, I would like to thank the organizers for the opportunity to give a talk at this online conference. And in my talk, I will speak about number of solutions to a special type of unit equations in two unknowns. Some words about the plan of the talk. This is joint work of my Japanese colleague Takafumi Miyazaki, and after a short introduction, I will give a brief summary of earlier results. After that, I will present the main result, and after that, the sketch of the proof of the main result. Let A, B, C be fixed coprime positive integers with the property that the minimum of A, B, and C is greater than 1. And the main object today will be this equation denoted by 1. We consider this equation A to the x plus B to the y equals C to the z in positive integer unknowns x, y, z. There are many results to this equation. The first result was due to Mahler, who proved that equation 1 has finitely many solutions. This result depends on the periodic analog of the Diophantine approximation method of Dewey and Siegel, and hence it is ineffective. The first effective result was given by Gelfond in 1940. Okay. We can easily see that our equation 1 can be rewritten in this form, x1 plus x2, using an appropriate substitution. Therefore, equation 1 can be regarded as an inhomogeneous S-unit equation in two unknowns over the rational field, but S consists of the prime factors of the product ABC. And in this regard, by a classical result of Kalman-Dury on the S-unit equation over number fields, one has it turns out that equation 1 has at most finitely many effectively computable solutions. And this means that the maximum of x, y, and z can be bounded by an effective constant depending only on the basis. The method is Baker's method, Baker's theory of linear forms in complex and periodic logarithms of algebraic numbers. Okay, I would like to present two other classical results on the number of solutions of S-unit equation. If you consider this S-unit equation where in S units x1 and x2 and alpha 1 and alpha 2 are given non-zero elements, then Evertsche proved a significant result on the number of solutions on equation S2. Namely, he proved that the number of solutions is at most this quantity here, where D denotes the degree of the field and S is the cardinality of set S. I would like to mention that the upper bound is independent of alpha 1 and alpha 2. One more result. Okay. We call two S-unit equations S-equivalent if alpha y over beta y is itself an S-unit for I equals to 1 and 2. And the classical result of Evertsche, Dury, Stewart, and Tiedemann says that apart from finitely many S-equivalence classes, equation S2 has at most two solutions. So this is a nice result. The upper bound for the number of solutions is really very sharp in one hand, but on the other hand, it is an ineffective result, and it doesn't give any information about the explicit number of so-called exceptional S-equivalence classes. But anyway, in view of the both general results, the number of solutions of our equation 1 can also be bounded. So if we denote by NABC the number of solutions in XYZ of 1, then of course Evertsche's previously mentioned result provides effective upper bound for the number of solutions, which depends on the basis. And as a straightforward consequence of a defined result of Boykers and Schlickaway, on the number of solutions of binary S-unit equations, Hirata Kono proved the following upper bound for NABC. Namely, she proved that NABC is at most this absolute constant. So this is the first absolute upper bound for NABC. Okay, the bound 2 to the 36 is although absolute, but it is far from the real order of magnitude supported by examples. Namely, I will give some examples here. If I choose 3, 5, and 2 for the basis, then it is well known that for this choice of basis, our equation has exactly 3 solutions. Then there are many cases and many choices of basis for which our equation has exactly 2 solutions. Moreover, for this choice of basis, we can see that there is an infinite family for which our equation 1 has exactly 2 solutions. So in view of the above examples, one can expect that apart from the above case, in which case we know that we have 3 solutions, hopefully this equation has at most 2 solutions. And in fact, this is exactly what we have done with my co-author, but of course I will come back to this point later when I will present our main result. Before presenting the main result, I would like to give a brief summary on earlier results on some special cases of equation 1, which are also interesting. So for example, if x is 1, then our equation becomes c to the z minus b to the y equals a. And if in equation 2 only a is fixed and c, b, z, and y are unknown integers exceeding so greater than 1, then equation 2 is exactly the Pillai's famous conjecture. And it is well known by the result of Mihailescu that if a is 1, then this is the only solution. But of course, for a greater or equal than 2, the conjecture is still open. Another previous result, if I fix the basis ABC and I take z and y only to be the unknowns, then after some classical results of Pillai and some results of Scott on the case c equals prime, Mike Bennett proved the following definitive result, namely, if a, b, c are positive integers with minimum cb greater than 1, then equation 2 has at most 2 solutions in positive integers z and y. So this is a nice definitive result of Mike Bennett. How to prove this? In the proof, Mike uses lower bounds for linear forms in logarithms of 2 algebraic numbers, together with the gap principle based upon some congruence arguments, which gives rise to a large gap among 3 hypothetical solutions. As I already mentioned, this result is essentially sharp in the sense that there are a number of examples where there are 2 solutions of equation 2. And I would like to note that the non-coprimality case, namely this case, is handled just by a short elementary observation. Now back to our original equation, and I would like to show you some earlier results on this equation. The first result seems to be the result of Sierpinski, and he solved completely the case where the bases are 3, 4, and 5. Namely, he considered this case of primitive Pythagorean triple, and he showed that in this case 2 to 2 is the only solution. In the same year, Jasmanovic extended Sierpinski's result, obtaining the same conclusion for these primitive Pythagorean triples. And after that, Jasmanovic formulated his conjecture, namely, if a squared plus b squared equals c squared, then equation 1 has only the solution 2 to 2. So I would like to emphasize that there are lots of papers concerning some special, many special cases of Jasmanovic's conjecture, but this conjecture is still open in general. After some significant works on our equation 1, Terai formulated another conjecture, which is an extension of the conjecture of Jasmanovic in the following sense. If a, b, c, p, q, r are fixed positive integers satisfying this equality with these properties, then equation 1 has only the solution p, q, r, except for 2 cases, in which case we know that there are exactly 2 solutions. Of course, in its full generality, this conjecture is still open, since it contains the Jasmanovic conjecture. But in some cases, for example, if PQR is exactly 2 to R, so this covers also this also covers the case of Jasmanovic conjecture. It is easily seen that the basis can be parameterized in this form, where m and n are integers, and r and I denotes the real and imaginary part of this complex number, respectively. And using this notation, I would like to mention a nice recent result of Miyazaki, appeared in Acta Arithmetica, which is the following. Suppose that PQR is 2 to R and R is 2 mod 4, so it covers the Jasmanovic conjecture, and assume further that this holds. Then there exists an effectively computable constant C such that Terra's conjecture is true whenever M is large enough, I mean larger than this constant, which is effective and depends only on R and N. And as a consequence of this nice result, Miyazaki derived the following corollary. For any fixed n, which is n, where n is 3 mod 4, Jasmanovic's conjecture is true, except for only finitely many values of m. So this is a nice progress in solving Jasmanovic's conjecture, I think. Okay, and now some more earlier results on our equation, which will be used explicitly in our proof. So the first covers the case C equal to 2. We turn back to our equation 1, and the theorem of Scott says that if C equals to 2, then equation 1 has at most one solution, except for these two cases, in which case we know exactly that we have 2 or 3 solutions respectively. Another important result is the case where C is odd on the right hand side in our equation 1. Namely, if C is odd, then equation 1 has at most 2 solutions. So this is a very nice definitive result and covers the case C odd. But the method of the proof is skillful and elementary, and mainly uses the theory of quadratic fields, but it works only for C odd. So therefore, for C even, also other method is needed. And before stating the main result, 2 more quantitative results in the following sense of Hu and Le. Namely, if I consider equation 1, then the first result of Hu and Le says that if the maximum of ABC is large enough, larger than this constant, this is a Baker type constant coming from Baker's theory, then equation 1 has at most 3 solutions. And this result was recently improved to this one. If the maximum was of ABC is larger than 10 to the 62, then equation 1 has at most 2 solutions. This paper appeared last year in Publicaciones Mathématiques Debrecen. Okay, so how to prove this? The main point was that some elementary methods, including congruencies, modulo powers of single base number, together with the theory of continued fractions, show that there is a large gap among 3 hypothetical solutions. And this gap principle was combined with Baker's method, and finally Hu and Le was able to prove such a quantitative result. And now I would like to present our main result. We actually, together with my co-author, we removed this assumption here. Namely, we have the following result. Consider our main equation, then equation 1 has at most 2 solutions, except when A, B, C is 3, 5, 2 or 5, 3, 2, in which case, of course, we know that there are exactly 3 solutions. So, as I already mentioned to you, the exceptional case comes from these identities. Moreover, our result is essentially sharp in the sense, sharp and definitive in the sense that there are infinitely many examples allowing equation 1 to have 2 solutions, as I already mentioned. So you can see here the infinite family having exactly, for which our equation 1 has exactly 2 solutions. Now, in what follows, I would like to give some details of the proof. In the first part, I would like to give the main steps and the main ideas of the proof, and after that, also some details. So, the proof of our theorem proceeds under the assumption that the maximum of ABC is at most this number, okay, and C is even. And in fact, there are 4 main steps. There is a general step. This is step 1. We needed to improve the bounds for the unknowns, for the exponential unknowns x, y, z in terms of ABC. And we did this, we applied very carefully the theory of linear forms in two adic logarithms. We could use this result. In fact, we used the sharp result of Bugeaud, and we could use this result because, as I said, C is even, so we can suppose this, and therefore we could use this result. But we really worked very, very carefully, and as a consequence, we obtained improved upper bounds for the unknowns x, y, z, which are logarithmic in terms of ABC. I will come back to this point later. And after this general step, we assume that we have 3 solutions. So our equation has 3 solutions. Without loss of generality, of course, we may assume that Z1 is less than or equal than Z2 and less than or equal than Z3. So in fact, we deal with this system 3. And under assumption 3, under the assumption that we have 3 solutions, the second step is to find sharp upper bounds for all the exponential unknowns of the first 2 equations in 3. So that's the main idea. Namely, we obtain sharp upper bounds for the maximum of Z1, Z2, and the maximum of X1 up to Y2. And in this step, we avoided the use of Baker's method. This was done elementarily by basically comparing the 2 adic valuations of both sides of each of the 3 equations occurring in our system. And I also come back to this point later. The third step, the third important step, was to improve somehow the gap principle in the corresponding previously mentioned work of Hu and Le. And under assumption 3, namely under assumption that we have 3 solutions, the main idea to improve the gap principle of Hu and Le is to consider 2 congruencies simultaneously. Maybe you remember I already mentioned that they used only 1 congruence, but we used congruences, some congruence arguments simultaneously by using modulus of each powers of the base numbers. And finally, this let us that, namely, we can say that under assumption 3, we worked out the above 3 steps and combined them with several other number theoretical methods. For example, some known results about ternary equations of various signatures to obtain sharp upper bounds for all letters occurring in the first 2 equations of the system 3 under the assumption that we have 3 solutions. And finally, in each of the above cases, we checked whether the first 2 equations of the system 3 hold or not. And at this point, I would like to know that although the derived general bounds for all letters in the first 2 equations of 3 are relatively sharp, I will give you a lemma, and you will see this. A direct enumeration of the solution is impossible. So therefore, we worked really very carefully and found efficient methods for solving the system formed by the first 2 equations in a reasonable computational time. Okay, and now before going into the details, by some earlier results, we may assume without loss of generality that we can suppose these. So these come from earlier results. So you can see here, for example, that C is even, C is greater than 2. This comes from the aforementioned result of Scott and Steyer. This lower one comes from a recent result of Bennett and Villeray, and so on. So this is the setup in some sense. We denote by alpha and beta some 2 adic valuations, the 2 adic valuations of some numbers. The beta is just the 2 adic valuation of C, which is greater or equal than 1, since C is even. And now some details about the general upper bound for Z, general Baker type bound. So since we would like to give for Z an upper bound, then since C is even and Z is large enough, we may suppose this, it follows that at least what is important here is that at least one of x and y is odd. And then by denoting by lambda a to the x plus b to the y, then of course, because of our main equation, lambda is also c to the z, and z can be expressed in this form, where on the right hand side we have the two-odd evaluation of lambda. So this is trivial, this comes from our equation. The non-trivial part comes from the careful application of a result of Bujold on lambda, and this yields a non-trivial upper bound for the two-odd evaluation of lambda, and therefore also for z. So we have the following lemma. After some technical assumptions, you can see here, we have for z an upper bound denoted by capital H, depending on several parameters. But what is important here is that the dependence on the basis is, of course, logarithmic, sometimes double logarithmic in this sense, times log A, log B. This is in one hand. And on the other hand, the explicit constants C1, C2, and C3 are as sharp as possible. So I will give you now the precise definition of C1, C2, and C3. At the first sight, it looks a bit strange and complicated, but the only thing what we need to know here is that as alpha and beta increases, then the values of C1, C2, and C3 are better and better. So just to compare our result with the previously mentioned result, the corresponding result of Hu and Le, you can see here is our result for the upper bound, and here is the corresponding result of Hu and Le. You can see here that for us the dependence in the log m's are also better, and also the constants are much better here. And this point was really very important at the enumeration step, at the computational step. So this was really an important improvement in this sense. Okay, now the second step, some details about the second step, is to obtain the first sharp upper bounds for the solutions of the first two equations of our system 3. And this is, to proving this, the key ingredient is the following elementary lemma. Suppose that we have two solutions, then in one hand this difference is non-zero, and on the other hand, the minimum of these two z's, the minimum of z and z prime, can be bounded by a bound which depends on the previously defined alpha and the two-odd evaluation of this quantity. And you can see here that, okay, just using Baker's method, we can give an upper bound for this quantity which is logarithmic in the maximum. And here one has the two-odd evaluation of this logarithmic function. This means that we have log something. So this is, in concrete examples, this is really very small and a good improvement, which was very useful again at the computational step. And as a consequence, we get the following lemma, namely, under the assumption that we have three solutions, we obtain that in fact, the first two z's can be bounded by a constant provided by the previous lemma, and the largest one can be bounded by Baker's method. Now, if we combine these inequalities 7 and 8, we obtain the following, just to emphasize and just to compare. Okay, so we have, using this lemma, we have the following. The largest one, namely z2, is at most 230, and the maximum of x1 up to y2 is 4,300. And if we would like to compare complete, do you think it is possible to give a complete description of those ABC having two solutions? Yes, Gary, so it would be very nice, but as far as I know, maybe this method is not enough for this. This method is not enough for this. We have some other, so we actually have some work in progress together with my co-author, but namely, in some cases, under some assumptions on the basis, under some congruence conditions, we can prove that we have at most one solution. So this is, in some sense, a direction which is related to the Jasmanovic conjecture. But okay, but this is what can I say concerning your question? Okay, and now for fixed, okay, and the third point, the details of the third point is the improvement of the gap principle of Hu and Le. Here I just, there are some notations here, but the point here is that we always can, this equation can always be rewritten in this form, capital A to the x plus lambda times b to the y equals c to the z, where lambda is 1 or minus 1. You can see here the corresponding parameters. And the point is that if our original equation has a solution, this is equivalent to saying that equation 7 also has a solution. Moreover, for every possible tuple, the number of solutions of 1 and 7 are equal. And now we present our improved gap principle obtained for equation 7, and then, as we did in our paper many times, we applied it in our proof concerning equation 1. For our purpose, because of earlier result, it suffices to consider this gap principle and equation 7 under these assumptions. Either C, capital C is even or A is even. And we have these lower bounds coming from the aforementioned previous results. Now, the first gap principle covers the case. So the first gap principle works under the assumption that we have three solutions. And it covers the case where Z1 is strictly less than Z2. And if we denote by G to the GCD of X2 and Y2, we obtain this divisibility relation. Moreover, if lambda is 1 or is minus 1, but G2 is large, then we have an upper bound for C to the Z2 minus Z1. Namely, we have a constant part here and the same part, the absolute value of the same quantity on the right-hand side. I would like to remark something here. This is really a gap principle. I mean that this quantity on the right-hand side can be bounded by Baker's method by a bound which is logarithmic in C, maybe log squared C or something like this, if C is the maximum. This is a constant part. And of course, therefore, on the right-hand side, we have something which is logarithmic in C. But since Z2 is strictly greater than Z1, on the left-hand side, we have something which is polynomial in C, and therefore, we have a gap principle, of course. To compare, I would like to show something about the corresponding result of Hu and Le. In the corresponding result, Hu and Le proved a similar result, but they could prove only this this divisibility relation leading to this upper bound. And in one hand, we replaced this factor here, y2, with the GCD of x2 and y2. And on the other hand, the constant term I already mentioned to you is very close to 1, where G2 grows and Z2 minus Z1 is small. And in fact, it turned out from our proof, it is clear that these were the most hardest cases. So, as I told before, if C is the maximum, for example, then our improved Baker type bound provides a bound also for this, which is logarithmic in C, and therefore inequality 10. In fact, the gap principle leads to an improved upper bound for this quantity and also for C and Z2 minus Z1 as well. And in order to obtain bounds for C and Z2 minus Z1 as sharp as possible, we can iterate the use of inequality 10, so our gap principle. Okay. Some very few words about the second gap principle. The second gap principle works under the same assumption and covers the case where Z1 equals to Z2. And you can see here we obtain also a gap principle. The proof is similar of the proof of Hu and Le, and the proof here uses also the theory of continued fractions in this case. Okay, now back to the method of the proof. Assume that our equation has three solutions. You can see here the system. We may assume without loss of generality that Z1 is less than or equal than Z2, less than or equal than Z3. And corresponding to this ordering, of course, we can order the corresponding xi's and y's in this form, as you can see on the slide. Moreover, we denote by dz, dx, and dy the difference of the first two quantities, and g2, gx, and gy are the corresponding great common divisors. Okay. Great common divisors. And now we distinguish between four cases. The following four cases. Case 1, Z1 is less than Z2 and C is the maximum. C1 is less than Z2 and C is not the maximum. Z1 equals to Z2 and C is the maximum, and Z1 equals to Z2 and C is not the maximum. And in what follows, I would like to give the details only of case 1. You can see on the right-hand side the corresponding Baker-type bonds coming from the previously mentioned work of Hu and Le. A bit motivation. Of course, in the case Z1 equals to Z2, the bond is much larger, the Baker-type bond is much larger, but we have this extra information that Z1 equals to Z2. So arriving to the computational and the enumeration step, it turned out, although we have 10 to the 62 on the right-hand side here, that this case was a bit easier. And this is the reason why I choose to go further with case 1. Okay, suppose that Z1 is less than Z2 and C, we have this Baker-type bond for C. Then, without loss of generality, because of symmetry reasons, since we know that C is the maximum, we may assume that we are in this case. Moreover, we have uniform lower bounds also for A, B, and C. These lower bounds come from the previously mentioned earlier results on equation 1. And now, by applying our improved gap principle 1 to our system of equations with these choices, we obtain the following. C to the dz, dz is at least 1, since dz is the difference between Z2 and Z1, is smaller than, this is a constant part here, times Z2 and the Baker-type bond, which is logarithmic in C, and this is very important. And for G2 equals 1, we use directly this gap principle. If G2 is of moderate size, I mean between 2 and 11, then by combining some known results on ternary equations of the signature x2, y2, and z2 with the first sharp upper bounds for the maximum of x, y, y, and z presented in the third subsection, we get a sharpening, a bit better result, and we use it. And basically for G2 greater or equal than 11, we use again the same gap principle, which I denoted now by relation 12. And now how to proceed? We apply many times this gap principle. We put MC to be the initial Baker-type bond. Since Z2 is at most this small constant here, and C is between C0 and MC, then our gap principle in the first step implies a small absolute upper bound for the difference Z2 minus Z1. After that, by the definition of beta and lambda, we have these upper bounds, the corresponding upper bounds for beta and lambda, which are logarithmic in MC, so not too large. And now it comes a tricky step. Since Z2 is Z1 plus DZ, and DZ we know that it is already bounded, then we use the elementary result presented in the third subsection to derive for each given parameters, beta, alpha, MC, and G2, a sharp upper bound for Z1, and also for Z2 in this way. So in this way, we get a much better bound than this 230 here. And after that, for each given tuple DZ, beta, alpha, and Z2, we use inequality 12 again, so the improved gap principle with this upper bound for C to obtain a new upper bound for C. And we iterate the above process. And Finally, as a result, we find a list of finitely many possible tuples dz, beta, alpha, and z2 with a corresponding upper bound for C. Just to show you, I would like to show you a proposition which I called sharp bounds, which comes from the iterating use of the previously mentioned gap principle. We obtain the following. Assume that dz is greater than 0. Of course, we are in this case. This is the difference between z2 and z1. And c to the z1 is 0 mod 4. This holds when z1 is greater or equal than 2. So this is a typical case. Then, if g2 is 1, then for these parameters, we have these bounds here, together with the upper bound for c. If g2 is greater than 1, we write to these bounds, together with this upper bound for C. And if this is greater than 1, so at least 2, then we have a very good bound for C. These bounds are really very good. So you can see here. And also the improvement for C. So in fact, we obtained for C, for the maximum of the basis, middle-sized bound, how to say. And consider the system, and now consider the system formed by the first two equations. And I would like to mention that although the above, and now at the end of my, so in the last part of my talk, I would like to speak about the sieve methods. Although the above proposition provides sharp upper bounds for Z1 and Z2 and middle-sized bounds for C, a direct enumeration of the solutions, I mean a kind of brute force search, is impossible in general. Of course, there are some cases, for example, if C is small enough, or Z1, Z2 is not too large, to use some kind of brute force search, and to guarantee that our system formed by the first two equations has no solutions. And therefore, we may suppose that C is large enough in this sense. The difference of Z2 and Z1 is 1, so this is the hardest case. And Z2 greater or equal than 4. Then we use some elementary arguments together with the bounds presented in the third subsection, and these results and these arguments imply restriction on x1 up to z2. I mean, we found many divisibility conditions and some inequalities, and in particular we found that if our system formed by the first two equations has a solution, then x1 is less than x2 and y1 is less than y2. So this must hold. Okay, and now finally I would like to show you two lemmas which are the main components of our sieve method. The first, under the hypothesis of proposition sharp bounds, if our system has a solution x1 up to z2, then the minimum of a to the x1, b to the y1 is greater or equal than c, and more or less the same holds for the other. Now I would like to show you very, very briefly to illustrate the method how to show that a to the x1 is greater or equal than c. Okay, suppose the contrary, and if y1 is less than or equal than z1, then a trivial elementary argument leads immediately to a contradiction. Therefore, we may suppose that y1 is greater than z1, strictly greater than z1. But then, from our equation, we see that this quantity here, c to the z1 over 2 minus b to the b1 over 2, must be between 0 and 1. By rearranging this inequality, we get, and expressing c, we get a lower and an upper bound for c, and you can see here the definition. And the point here is that since y1 is greater than z1, it happens very often that the lower bound is greater than the upper bound for given b, y1, and z1. So this means that for given b, y1, and z1, the number of candidates of c which can come into the game is very small. In many, many cases, the number of such c's is 0, making our C method very, very efficient. And using this idea, together with sharp bounds, the proposition sharp bounds, we have a list of all possible tuples, alpha, beta, z1, cu, where cu is the corresponding upper bound for c. And for each such tuple and for each possible tuples, in fact, we implemented the above idea in some program package. And finally, using this relation, that Z2 equals Z1 plus 1, we checked that this equation holds or not. But it turned out that it doesn't hold. So therefore, we must have this inequality, a to the x1 greater or equal than c. And the remaining inequalities, of course, can be shown exactly in the same way by changing the roles of A, B, Z1 and Z2 respectively. And the final lemma, under the hypothesis of proposition sharp bounds, if our system formed by the first two equations has a solution, then we must have this inequality here, namely x1 greater or equal than x2. Just very briefly, again, suppose the contrary, and the case where y1 is less than y2 can be ruled out by our system of equation and the previous lemma. Therefore, we may assume that y1 is greater or equal than y2. And system 13 with z2 equals z1 plus 1 leads to the following chain of inequalities. Namely, we have a very good lower and a very good upper bound for A. And in view of these relations here, we obtain this lower bound and this upper bound for A. So this means that we used, in fact, more or less the same idea as before. This means that for given parameters, you can see here on the left-hand side, this factor is the same. And for given parameters, as the parameters grow, then this is also close to 1 from below, and this constant is also close to 1 from above. Where here you can see the definition of A1 and C2. And therefore, for given parameters, the number of A's coming into the game is also very small, making our C method very efficient. And now, how to proceed, how to use this idea? Proposition sharp bounds provides us with a list of possible tuples, beta, alpha, Z2, and Cu. And for each element in C list, we use the previous lemmas to sieve considerably the possible solutions x1 up to Z2 of the system 13. And this way, we obtain a list named list 1, having elements of this form, containing all the necessary data, the parameter alpha, beta, the possible solutions, and the corresponding upper bounds Cu and B max. Where B max is the corresponding upper bound for B. Okay, and then in order to create our list 2 containing all the necessary data A, B, x1 up to Z2, we just implemented the above presented idea. And here you can see this is the key point, the lower, and in the lower and upper bound for A, we put in these two constants here, these two bounds, making this this program very efficient. And as a conclusion, we get that under the assumption that x1 is less than x2, no solution to this equation is found. Thus, we obtain that under the hypothesis of proposition sharp bounds, we must have that x1 is greater or equal than x2. And in a completely similar way, we also get that under the hypothesis of proposition sharp bounds, we also have y1 greater or equal than y2. Okay, but these two informations together contradict the fact that the system 13 can have a solutions only with x1 less than x2 or y1 less than y2. So in fact, this is the end of the proof. One more remark at the end, that the total computational time of all programs implemented in program package Magma took about 25 hours on a usual laptop. So, and this is the end of my talk, and I would like to thank once again the organizers for the opportunity to give a talk here, and thank you very much for your attention.